We're gonna look back at hypothesis testing using a SET test. And keep in mind, the confidence intervals and hypothesis testing are somewhat related, because confidence intervals are basically the probability of this being either significantly different or not significantly different minus our alpha. And the alpha is basically the acceptable risk of being wrong when we're saying this is significantly different. So that we actually were saying something is significantly different, although it's not. So basically, this is the comparison distribution for a SET test. Is basically the distribution of the means. That means that we have a sample mean, and we are building the so-called standard error of the mean, utilizing information from the standard deviation of the population by dividing the standard deviation of the population by the square root of the n of the sample size at hand, assuming that when the sample size is large, there will basically a lot of variability between mean estimates of samples of that size, and there will be a lot of variability. Whereas if it's small, there will be more variability. And the standard error of the mean is important because it characterizes this distribution, the distribution of the means. And in the end of the day, with hypothesis testing, we're calculating the difference between the sample mean and the population mean, and we're standardizing this, following the standardization principles that we've discussed with the populations, with the standard error of the mean as this variability of the distribution of the sample means. So it's important that you always keep this in mind. This is the standardized distribution of the sample means, or the differences of this. But in a SET test, you have a lot of mean estimates that are distributing with a certain standard error of the mean or a certain variability, and you're subtracting. Even after it's standardized, you're subtracting a constant from it because the population mean doesn't change. So it doesn't make a difference at the end of the day. And you're standardizing this as per the standard error of the mean, and you get those critical values beyond which you're basically looking at a significantly different distribution. And you could still make a wrong assessment, but it is smaller the larger the set score is. So when you look at our example, and now let's go back to that example we did in module 9, which was the cholesterol example. So if we're doing a SET test, we essentially were calculating our set by subtracting our population mean from the mean of the sample. And then we're standardizing it as per the standard error of the mean, which is sigma population standard deviation divided by the square root of the n. So we have 195 as our sample mean, our x bar, minus 211, which is the population. It's not stated here, but that's what it is. And then we're dividing it by 46, which was the standard deviation divided by square root of 25, which is a sample size. We're getting to a set of minus 1.74. Looking that up on our distribution table shows us that minus 1.74 is 0.0409. So that's exactly that p-value. This is a percentage of our overall population. This is in the context of a population. It was the amount of people in New York City that had a blood pressure between 120 and 140, if you remember that example. Not the best example, but it's a memorable example. So we have now 0.041 as a probability of our population mean falling within that assumed modeled kind of distribution of the means. So this probability of 0.041 is only the left tail. In a two-tail test, we need to multiply it by 2, gets us to 8%. This 8% probability is is larger than our 5% that we're willing to accept. Therefore, we are accepting the null hypothesis and not rejecting it. That would be notably, because it's a two-tail test, if 195 would be replaced by the second sample, and that would be 227, the result here would be plus 16 and not minus 16, and that would give us a positive set. Because it's two-sided and symmetrically, we would need to quantify the tail to the right. And that is with plus 1.74, and don't fall into the trap, please. If you're being challenged on a question on an exam with that. If you do 1.74, you're basically looking at 0.9591. 1, the whole thing, minus 0.9591 is 0.041. And you're multiplying that by 2 again, gets you again both sides. Where it's getting tricky, and we discussed this in the practice lab, and that's the example. That's why I think this examples we did in practice lab was so important, because it basically allows you here to look at directional hypothesis. If you have under the null hypothesis, you have an X bar that is greater or equal to the population mean. Your corresponding alternative hypothesis under this, the X bar needs to be smaller than 2. The testing will basically be done in the same fashion. You calculate the same set score, but what's different now is that you basically have the tail only to the left, following your research hypothesis. And that is very important, because if you're calculating a positive set score and your hypothesis is actually so unrealistic that your mu is actually substantially larger than your 211 and your population mean, you will get a lot of black solid area, solidly filled area. And that's the case here. If you reverse this hypothesis, you basically get here under the null hypothesis, you get mu by X bar smaller than 211. Under the research hypothesis, you get the X bar, the sample mean being greater than 211. You basically need to quantify everything under the curve to the right, irrespective of the value. Just make sure that you understand these concepts, and I highly recommend to sketch out a normal distribution curve on a piece of paper, to be honest, because you may get confused on the exam. Okay, in this context, it's also important to keep in mind this table. And Norton and Heinzen basically have the same table. So basically you have a true state of nature. So you know the null hypothesis. So let's assume it's given that the null hypothesis is actually true and the sample mean is not different from your population mean. And in the second possible scenario, the null hypothesis is actually false. So let's assume this is true and you're rejecting a null hypothesis. You're basically committing a type 1 error. If you should have rejected the null hypothesis because it's actually false and you don't do that, you're committing a type 2 error. And that's an acceptable limit that you define yourself, because that determines the resultant of 1 minus the error. So if you have 1 minus the alpha, this is your confidence interval, as you know. So that's actually the probability that the null hypothesis is actually true. So if you have a type 2 error and you want to have actually an estimate of so-called power, which is 1 minus the type 2 error, 1 minus the beta, you essentially have false null hypothesis and you're really rejecting it. What's important in this context, and that's to be emphasized here, is that statistical power can be affected. And it's basically determined by the population mean, population standard deviation, the sample mean, sample size, the resulting standard error, which is basically a function of the sample size. So why is this important? Because when you study any given research question and you design a study that allows you to investigate this research question, you need to estimate how many individuals you actually have to study. And that is basically determined by a sample size estimation, which is done in the context of power calculation. So that's why this is important. And there are ways how you can actually affect power. And the way to affect power is by increase your alpha, which makes sense, right? Because you essentially, you're now willing to accept a higher risk that you're actually wrong, that you're more likely to reject, although it could possibly be wrong. You turn a two-tailed hypothesis into a one-tailed hypothesis, which goes in the same direction in a way. You increase your N, which decreases your variability, or you exaggerate the mean difference between the levels of the independent variable. So if you increase the alpha, so when you think about it, everything that is from the second comparative, in the second distribution that you compare the first distribution to, you basically have everything exceeding that threshold, the critical threshold, that is not part of that alpha, where you rejected, which you shouldn't have rejected. That's your true rejection region, so to say. This is where you exceed that critical cutoff, but you're basically not part of that alpha. So that is your power. If you increase that now to 10%, you basically increase also automatically your power region. If you change a two-tailed hypothesis to a one-tailed hypothesis, in essence, you're doing the same thing. You're just shifting it on one side, both tails. If you increase the sample size or you manage somehow to decrease the standard deviation, you're again doing the same thing in a way, because what you do, you decrease that overlap. So basically, by getting the distribution skinnier, you have a larger area that has greater power. If you increase the difference between the means, you essentially do again the same thing. You increase that area that is not overlapping and you minimize the overlapping regions. So these are actually very valuable graphs that I highly recommend to review and think through in much detail. Okay, any questions to that? We talked about it already. We talked about meta-analysis. Just as a last reminder in that regard, so there's effect size. So that's Cohen's D. So keep in mind when we calculate, and we've just seen this formula, when we calculate our set, that basically leads us to hypothesis testing. We're calculating the difference between the sample mean and the population mean, and we're standardizing this by the standard error of the mean. So we're basically standardizing the differences. If that set is exceeding that critical value, we're rejecting it. What the problem of the standard error of the mean is in principle is it is strongly affected by the sample size. Logically, conceptually, because a larger sample size will more likely reflect the true population mean, firstly. Secondly, if you have a more accurate estimate of that population mean, you will also have consequently less variability in your sample variability. If you draw 100 samples of a certain size and then 100 samples of a greater size, 10 times as many people, you will get less variability because a larger sample size will basically be a more accurate reflection of your population mean. So that variability decreases conceptually and also arithmetically because you're dividing it by the square root of the n, which will automatically lower your estimate by just having a larger number in the denominator. So this being said, if you want to quantify the effect size, the true effect size independent of the sample size, you need to have an accurate estimate of your standard deviation, which in the context of a set test is given to you by the population standard deviation. And then you're basically calculating the difference between the sample mean and the population mean, and you're standardizing as per the standard deviation of the population. And that D can then basically be interpreted in the realm or in the magnitudes that are suggested by Cohen's conventions. That basically associates with a certain overlap of a perfectly shaped normal distribution. Good. Any questions on effect size? No? All right. So now, I've said it quite repeatedly now, you have a standard deviation that is given from the population. So that's for the set test. So now the t-test actually brings that to the next level, because now we're looking at a t-distribution. And the t-distribution is actually not strictly identical to a normal distribution. It's an approximation of the normal distribution. So we mean to resemble the normal distribution and have an estimate that kind of allows us to interpret data in the same fashion as a normal distribution. So we are estimating the standard deviation of the population based on the variability and the standard deviation in our sample. That makes a huge difference, because the standard deviation of the population, if you want to know the standard deviation of the population of the New York City population, good luck measuring 50 million people. So you cannot measure it because it's just logistically and organizationally not possible. So you need to have some shape or form, some way how to estimate it. And so I always found it kind of amusing that actually came from beer production. So the person who actually estimated that method was actually William Gossett, who was the head brewer of Guinness, who came up with the insight that when you want to keep a certain quality standard in your beer, and you can't really test the entire production of beer, you can't go and open all the bottles and measure them and then reclose them. That's not feasible. So they basically, what they did experiments measuring the entire day of all the beers. And then they basically took small little batches and measured the variability within that batch and used those estimates of the variability in the batch to find a way to estimate the variability in the entire beer production of the day. So that actually was the impetus and the start of t-distribution. And that's how it found its way. So that was in the end of the 19th century, they came up with this idea. So the t-distribution is with us because they wanted to brew good beer in the UK. And it's since one of the most often used statistical methods that you could think of. It's basically, it's used in every context, and it's the most commonly employed technique. But yes, that's where it comes from. So it's beer production. But it's being used as a t-distribution is like estimating the variability of a population based on a little batch. You can only think of the examples, but this is actually used for. This comes from car production, every factory process, everything that produces something in a systematic, multiplicative, replicative way will use the same principle. So you're estimating the variability of your quality. So this being said, when we look at this distribution, we see here the blue one is the standard or normal set distribution. And we see that with an increasing number of sample size, this will become more and more shaped and formed like that set distribution. So this basically is essentially true up until the magical number 30, which is kind of used by statisticians to kind of as kind of a threshold. When you have a sample that exceeds 30, you get away using set distribution values, critical thresholds from set distribution. So up until 30, you're asked to use t-distribution rather than set distribution. And you see basically how the shape changes. So you see basically that it becomes taller with the normal distribution and with an increasing sample size, and it also kind of narrows a bit more. So it actually is wider with the lower estimates. And nevertheless, the estimate is only slightly modified. So what you essentially do, and we have discussed this equation for the standard deviation when we talked about populations. We have a standard deviation that is calculated as the individual deviation from the mean. So each individual score, we calculate the deviation. We're squaring each individual deviation and we're summing them up, gets us to the sum of squares. That's actually here in the denominator. We're dividing it by the sample size, gets us to the variance. We're employing the square root, we basically get to the standard deviation. Now we're doing the same thing, We're calculating the sum of squares, but now we're not dividing it by the sample size. We're dividing it by the degree of freedom. And that's conceptually, it is serving the purpose of a modification to make the t-distribution with a certain sample size more comparable to the normal distribution. It changes the function pretty much. It changes, if we remember the normal distribution function, it means to resemble the same shape, but the modification here is basically these degrees of freedom that allows the standard deviation to be kind of like estimating that of a normal population and then being used for the normal distribution, the shape of the normal distribution. And that's the relationship you're looking at here. So keep in mind, you're dividing now by the degrees of freedom, and then you're employing the square root, and then you get from the variance to the standard deviation. It's a minor difference, but these degrees of freedom with small sample sizes, it has a lot of weight logically. And you see that reflected in the new table that we're going to look at today. We're moving now from a set distribution table to a t-distribution table. And you see that with the small numbers and the small degree of freedom jumps, so from degrees of freedom of 3 to 4, the jump in our critical values is much more prominent than with the larger numbers, where it basically approximates this normal distribution. So it takes on the shape of a normal distribution with higher numbers. So the degrees of freedom conceptually are to be seen as a redundant number that can be dropped, knowing the sum of squares and all numbers in a system. You can drop one number and you still can preserve this one number. So you can drop this one number without having actually information loss from your data set and the resulting sum of squares. So it's kind of, if you have an entire list of numbers and you know the resulting sum of squares, and then you drop that last number, you can reproduce that last number. So that's conceptually how they looked at these degrees of freedom. It's a redundancy that was removed in the knowledge of the resultant sum of squares. So, well, the calculation is super simple, right? And of course, we have an example today. I like my examples. So we have today, who of you ever worked in an office? So, you know, it's when you work in an office and you're being interrupted from a task that you really need to focus on, you're being thrown off for a long period of time. That's why, like, the first thing is like, you need to concentrate on a task. It's like phone, silent, vibrate, do not disturb, and switch off Teams and whatever messaging service. Otherwise, you can't focus, because whenever you're being interrupted, it takes you time to basically get back to the task and immerse yourself in that mindset of the task that you've done. So Mark, Gonzalez, and Harris studied in 2 high-tech companies for more than 1,000 hours of employee time. If you have employees that spend 11 minutes on average on one project before being interrupted, after each interruption, they need an average of 25 minutes to get back to the original project. So maybe the reality is that multitasking overall reduces productivity. That's well understood. So suppose you were a manager at one of these firms and decided to reserve a period from 1 to 3 each afternoon during which employees could not interrupt one another, but might only be interrupted by people outside of the company. To test the intervention, you observe 5 employees and develop a score for each time spent on a selected task before being interrupted. Here are the fictional data, 8, 12, 16, 12, and 14. In this case, we treat 11 minutes as the population mean. So we know that our population mean is mu, 11 minutes. We're comparing now our data entries of our 5 employees to a mu of 11. How are we going to do that? We're basically calculating first what the sample mean is, right? We want to know our X bar. And this is basically average of 8, 12, 16, 12, 14. Gets us an X bar of 12.4. It's just the average function. Just the average function. So Now what we want to know next, what we want to know next is our deviations. And that is 8 minus our x bar. So let me do 9. That's our deviations. Next, we need the squared deviations. That's basically this squared. And then we're summing this up. And that gets us our sum of squares. So, it's not good. Okay, squared deviations, sum of squares. This formula is essentially, so some squared deviations you can also express like this. You can put this in a bracket. And just square everything. Good. So this is our sum of squares. From the sum of squares, we want to know next. So we know now that mu is 11, n is 5. This equals count from B3 to B7. Now with degrees of freedom, I abbreviated this df. That's basically our n minus 1. And our sum of squares gets us to the variance. The variance is now our sum of squares divided by the degrees of freedom, 8.8. Our standard deviation is now the square root of 8.8. It's 2.97. So that's our standard deviation. Right? I can this. This. That basically gets us down to the standard deviation. Alternatively, you can also express it as STDEF dot STDEF of E3 to B7 gets us to the same result. And that's where the difference is. You remember, some of you, that STDEF.P, STDEF was STDEF.B. We did that comparison. So this is the standard deviation if we would treat this as a population. So that's using the actual sampling. You see there's a substantial difference, right? That's like a 10% difference. So that's not trivial. So now that we have this, what do we need to do next? So we want to compare now. So these are the 2.97. We want to compare now whether our sample is actually statistically significant difference from our population mean of 11. And this is where now the catch is, and I'm flagging this. Please do not confuse this, because that's just conceptually very wrong. Okay, so we have a standard deviation that was estimated based on our variability in the sample. I don't know where it does that. So this was now estimated based on the variability in our sample. What does not change? What does not change is the estimation of the standard error of the mean. So keep in mind, this was now divided. So this was sum of squares divided by the degrees of freedom, which is n minus 1. The standard error of the mean is still divided by the square root of the n, because we're not changing the method of estimating the variability of the distribution of the mean. That is still the same. We're just changing how we're estimating that standard deviation. And that's important to keep in mind. And that's, I've seen that quite repeatedly being confused as well. I'm explicitly mentioning it. So if we're calculating now our SEM, this is now standard deviation divided by square root of the n. if we're based on that, we want to know now next our critical T, right? And this is now where we're moving to the T distribution table. So that is also on your canvas. On your canvas are 3 files today in the module. In module 12, you have the slides, the Excel spreadsheet, and the T distribution table. On the T distribution table, just look at it in the same fashion as the STAT distribution table. It's the same principle. What's different now is you have here on the rows, you have the degrees of freedom. So you're following these along, and you have on the column header, you have 1 tail and 2 tails. And since we want to know a critically, now not a critically set, because it's not a set distribution, now we want to know a critical T. So for obvious reasons, the degrees of freedom are leading us now, because the function will be different with each different degree of freedom, because it's divided, the standard deviation is divided by n-1. So the degrees of freedom change with each change in the sample size. So the functions will be different that are resulting from the mapped normal distribution curve. Bless you. And if we look at the column header, we have our alphas again. So we need to find now the corresponding alpha we're interested in. And so since we're basically doing 95% of all the time, we do 5% in a 2-tail test. We're going for 2-tail for the rows, 2-tail. We're finding 5%, and we're just following downwards until we have the degrees of freedom that are corresponding with our example, and ta-da, that's our critical T. So if we have degrees of freedom of 4 and an acceptable type 1 error rate of 5%, we are at a critical T of 2.78. And that is what we will enter here, 2.78. So now we want to calculate our actual T, and that's simple. We just need to calculate now M, which is our X bar, minus the mu, divided by the standard error of the mean. And that gets us to a T of 1.056 or 55. What do we conclude now? Because the T is less than our critical T, that means it's within the boundaries of our critical T's. That means it's not significantly different from the null hypothesis. That means that the null hypothesis, which I should have stated before, which is H0, is M or X bar, M equals mu, where HA is M not equals mu. And now we're not rejecting the mu because it's not exceeding our critical threshold. So in this very context, it also makes sense to calculate the 95% CI. And that essentially is done here in the same fashion as with the SET test. We are calculating this by taking the average of 12.4 minus our critical T, our critical value, multiplied by our standard error of the mean. The upper limit is calculated in the same fashion. We're taking our X bar plus critical value multiplied by standard error of the mean. And that's our 95% CI. And as we can see already with the naked eye, just looking at the interval, we have 8.7 to 15.3 that clearly includes our X bar of 12.4. And that also not 12.4, actually includes our mu, wrong, not the sample mean, the mu. It includes our population mean. That means our population mean is right within our confidence interval. So we are actually quite certain that this is a correct null hypothesis. So essentially, we're not rejecting the null. H9, yeah. So, H0. Okay. So, and this is the example. So basically, it does not make a difference whether you place an intervention on your employees to not have them interrupted for 2 hours. Doesn't make a difference. I actually think it does make a difference, but that's a different story. Okay, but we would need to read the actual paper. Good. So this is how we're using t-distribution and t-test, right? So this is the first of 3 t-tests, because now we're basically at this point that we're comparing a sample. So we're not using we're using not the comparison of a sample with a given standard deviation. We're now exclusively looking at the sample. And now next time we will actually compare 2 samples. The following time we will compare 2 samples independent from each other. So it becomes an independent sample data. So it's going to get exciting now. We're getting really in the realm of like real analytics. So that those are tests that are just done on a daily basis. This is real statistics. Good. Okay. So we have now this we have, this we did. So it's important to know we know the population mean, we're comparing to the population mean, we don't know the standard deviation, we're estimating this using the degrees of freedom. We talked about this, except from the t-table. I do not like this t-table. I think there are better ones, and mine is definitely better. That's why I give you mine. We have the 6 steps of hypothesis testing, same structure as we had with the SET test, up until step 6, where we make a decision based on our t-values. And that's pretty much it. So now we do another example. Any questions now concerning t-tests? And is that recording? No, I don't know. Okay, so next example. We're doing a single sample data. Step 1 in hypothesis testing is always to identify the population, identify the distributions and the assumptions. Please make sure that you also understand operational definitions of what is an independent variable, what is a dependent variable. That is certainly something that will be on the midterms, that you will have a question in front of you and you're being asked, what is an independent variable in this context? So make sure that you kind of have a solid handle on that. And we can talk about this. We have a little bit of time later. Okay, so we have now population 1 is all clients at a counseling center for students, the student counseling center on a campus, who sign a contract to attend at least 10 sessions. So 10 counseling sessions, that is. So all clients sign a contract to attend at least 10 sessions. Population, so that's pretty much all students, right, that go to these counseling centers. The counselor is going to tell them, I want you to come to every session. Student says yes, walks out, and that was the last time you saw him. So then you have a second population that you basically have, and this is a common practice in these kind of softer sciences. You basically, you have the individual student sign a contract that he will attend all counseling sessions. If you just tell him like, I want to see you at the next session and I want you to come to our sessions, he walks out there, you're never going to come back. If you have him sign a contract that psychologically empowers him to take ownership of this task, and he or she will then come to the counseling sessions. That's actually quite often used in psychology. It's for example, behavior change. You have people, you empower people to embrace the change in their behavior by basically signing a contract with themselves and their therapist. It's actually quite successful. So we're doing this now, and we're testing this now with students that come to a counseling center on campus, and we're comparing the adherence to at least to attend these 10 sessions after signing a contract, and comparing it to the overall population of all students that came to the counseling center and they just walked off, didn't sign the contract. So we're comparing this now. Well, the overall population did also include these 10 that signed the contract, per definition, because they are a subset of these. So the comparison distribution is the distribution of the means for the standard error calculated based on the standard deviation estimate using the degree of freedom modification. It's a single sample t-test because we only have one sample. We don't know this actual standard deviation of the entire population. And the assumptions that we're doing is normal distribution, independent samples, and randomly sampled. So now the hypothesis. Clearly the hypothesis is, this is example 2 here. The hypothesis, the null hypothesis here is that X bar equals mu. And the HA is that X bar does not equal mu. Right? That's our hypothesis. We know the populations, we know the mu are all these 2,000 students that came to the counseling center. The ones we study are these 5 guys, five students. If we build an average, we basically know now the average for our sample population. And now we next calculate the deviations. We're calculating we're taking these deviations, we take squared deviations. We're calculating now these squared. We're summing this out. That gets us to the sum of squares. We're calculating now next the variance, and for that we need our n. Our n is basically count of these 5 entries. Our degrees of freedom is basically this minus 1. Our variance is basically this divided by this. And our standard deviation is basically the square root of this. So that's our standard deviation, and that's the variability from our, okay, so that's the standard deviation. Based on the standard deviation, we can now estimate our standard error of the mean, and that is basically now standard deviation divided by square root of our sample size. And please keep in mind to divide it by the square root of the sample size, which gives us a standard error of the mean of 1.14. Now, next we need to determine our critical t. The critical t is basically determined by our degrees of freedom, which again is 4, and our acceptable alpha, which is 5%. So we're coming back to a critical t of 2.78. We're calculating now next our t, which is basically our sample mean minus our mu divided by the standard error of the mean. Gets us a t of 2.87, which is exceeding our critical t. And we are now rejecting the null. We're calculating next a 95% CI, just in the same fashion we did before, which is basically nothing else but our sample mean minus our critical t multiplied by the standard error of the mean. And the upper limit is our sample mean plus 2.78 multiplied by 1.7. 10.9. So we have 4.70 to 10.9 is basically our 95% confidence interval, which denotes that region in which we're 95% certain our null hypothesis is actually true. And this is essentially including, bless you, this is basically not including our mu of 4.6, and thereby we are rejecting the null hypothesis. Yeah, makes sense, right? Makes sense? Okay, good. I like the agreement. Any questions on this?
Steps, that's why.
Well, but it's each of these steps, and I know and I understand that. And it's unfortunately, the unfortunate truth is by memorizing these steps, you will automatically memorize the concepts. And when you memorize the concepts, you know when to employ which concept. And I know it's the examples, that's why I try to go along with Nolan and Heinzen's example, and I try to give you the arithmetics with the example, because it makes it illustrates it more why this is actually important, that you understand each step, because it automatically leads you to how to actually use that method. That is at least my approach to it, because it is not, if I just conceptually tell you that, you're listening to me, you're looking at me, but it's like you will not retain it. By the calculation, by going through those calculations, you you see how things are coming together. That's why I'm teaching these examples the way I'm teaching them. And
How would you do this on a test? If this would take you so long. This would take you so long to do on a test.
yes, but at the test, you will only get a snippet of that. You're not going through the whole thing. You're not getting this. No, explicitly excluded the questions which would take you like good 5 to 10 minutes to calculate. But you could be asked, for example, calculating the standard deviation out of the sum of squares with a sample size of 10. I know.
And that's like quick.
It is quick. So, but the point is, you need to know where to start, right?
Yeah.
If you have not gone through those steps, you will not know where to start, and it takes you half an hour to figure out where to actually start calculating.
This is for homework type.
This is the homework kind of thing, and this is why it's also important that you do the homework, that you go along with those examples, because walking through the calculation steps, I know it's tedious, but it's like it makes sense for you to memorize it and to internalize it. Good. Any questions on any of this? I think it's quite simple to understand. Just make sure that you know how to read a t-square table, almost a guarantee question where you need to do that. Know the steps of calculations, and know what's the difference between standard deviation in the population and standard deviation in the sample. And that will be off the exam, I guess. Okay, so here just the calculation is Nolan and Heinzen. That's the confidence interval that Nolan and Heinzen shows. That's from minus 2.78 to plus 2.78. It has the two tails on both sides. And the t is basically in the critical region above the positive t of 2.78. As we have calculated it, there is no more distinction between positive and negative at this point. You can do a one-sided t-test, but you will need to adapt it accordingly. But it won't be really tested that way. Calculating confidence intervals we did, that's the calculation. Yeah, we have calculated this before. We know how to evaluate them. Keep also in mind that reporting the confidence intervals will also automatically allow for your reader to basically do hypothesis testing. Because if it's outside of these confidence intervals bounds for your sample, and you're calculating this interval for your sample, you can automatically allow the reader to do the hypothesis test without you talking much about it. I also want to draw your attention here on one thing that Nolan and Heinzen do that I don't really like, to be honest. they are basically calculating the actual confidence interval. That means like the numerical interval. And I'm not really sure I like that too much. But as per definition, we have from the mean to the upper bound and from the mean to the lower bound. This is the actual confidence interval in a way. That's the actual margin of error, as it's also called in many cases. I am not really a big fan of expressing that range alone because it doesn't give you the actual estimate of the interval, and you can't utilize it for hypothesis testing, only if you start adding and subtracting it from the mean. So I think the big thing is as an interval, an actual lower bound and upper bound is just the nicer way to do. But hypothetically, what they are doing here, they're saying, okay, so now we have this minus this. That's the actual interval. And so this is the lower margin of error. So this is basically this mean minus this. So that's the lower margin of error. And then we have the upper margin of error. That would be this minus the mean. So that's also a way how to look at this. And you will see this where you see the margin of error quite frequently. And I think I mentioned this in our first class together with the polling, the political polling. You will see in the news when it comes to elections, you will see survey results. You will see survey results for, I don't know, any TV channel called up 500 people. And we estimated that likely, I don't know, the representative for Senator XYZ will win over XYY. So we have then with these polling results, we have a margin of error, which is based on that sample and our estimated variability within our sample. We estimate this to be the result in the population that will vote on this particular election day with a margin of error that is calculated in that shape or form. So this is how you calculate that margin of error that you will see in the news. That's maybe just for general information more. Yeah, I personally don't like this much. I'd rather have the interval per se, but that's to each individual. It comes arithmetically to the same thing. Here in Norton and Python also point out that essentially for the interpretation, you can utilize confidence intervals to do hypothesis testing. So basically you have a 95% probability to have the population mean located within these two numbers, within that interval. And if it's outside, you are rejecting the null hypothesis at an alpha level of 5%. Also important, you can now calculate your effect size. And we know the effect size is being calculated in the same fashion as the t, by basically calculating our average minus our mu divided by the standard deviation rather than the standard error of the mean, because it is an estimate of this effect size that we're looking at independent of the sample size, because the sample size will affect the standard error of the mean and therefore will be unduly influenced by large sample sizes. So since we have a small sample size and we are interested in estimate of the effect size independent of the sample size per se, we are dividing here the difference by the standard deviation. We get an effect size of 1.29, which essentially is as per the conventions of Cohen, which I suggest you have a look at, a large effect size. So make sure you understand the effect size and why they're being used, bless you, and where in the conventions they fall and how you can classify them. Good. It's effect size. Any questions on effect size? Any aspects that we discussed? So then I quickly just want to talk about what we discussed before and what I mentioned before. So for the midterm, please do not underestimate the weight that chapter 1 actually has. And this is where I talked before about the operationalization of variables. So chapter 1 is chapter 1, right? So chapter 1 is like something you do in the beginning and everything sounds interesting and new, but everything sounds good, but it becomes more of weight moving forward with the chapters, because now if you do a t-test, a single sample t-test, what's the independent variable, what's the dependent variable, it's a precondition that you know that. So you need to understand these things. If you, for example, you compare two populations in terms of blood pressure, and they're both different by, I don't know, one likes dogs, one doesn't like dogs. What is the independent variable? Is it the blood pressure? Is it the size of the population? What is it? So so you need to understand what is the outcome, which there is blood pressure. What is the independent variable? And the independent variable is there having a dog or not a dog. And the definition there is that you have an independent variable with two levels. And that is for these t-tests that we will do moving forward. We will do a paired sample t-test on Wednesday, which basically is the same individual during 2 time points. So now we're getting to 2 sample comparisons. So we're having a sample of individuals. Let's say a student does exam 1 and the student does exam 2. You have the comparison from first exam to second exam. That is a paired sample t-test. You compare each student from the first exam to the second exam. You build the differences, and then you use the differences between these 2 exams as your comparison distribution. So that's what we do in the following now. So that's where we only focus on the sample. So we're dropping the population. That's over. With today's lecture, that's over. Now we're just looking at samples, and we're just estimating standard deviation. We don't have population standard deviations anymore. What's just really getting more important that you know these definitions of what is dependent and independent variable, because you have, for example, with the paired sample t-test, you have an independent variable, which is time, before and after. So it's time is your independent variable at 2 levels, before and after. The dependent variable is then whatever you have measured, be it blood pressure, be it scores, be it grades, be it, I don't know, happiness, whatever it is. That's why this becomes important. Then even in the next step, when we get to analysis of variance, which is from calculations, that's usually when most students are not very happy, because that's quite intense to calculate. So analysis of variance, you suddenly have like 3 different levels or 4 different levels. So you basically, but it remains to be that the independent variable is the one that has different levels. So that's why I'm coming back to that, because now we're getting further and further into the material, and it's important that you kind of have these basic terms memorized. So operational definitions are basically the way you define your variables and how they're being defined moving forward, and how you will include them in your analysis. So you frame a hypothesis, a research hypothesis, in a way that it is structured in a dependent, independent variable. And that I almost guarantee you that you will have questions on your exams that will ask you to define those and give a reason why. So the examples that Nolan and Heinz give here is research question here, for example, could be, does having a pet increase your happiness? And you do this in your population, and you're basically defining as your outcome variable the level of happiness in a population. And as your independent variable is pet ownership, yes, no. That's how you deduce this information from your question or from the text that you're reading. Are people that smoke cigarettes, do they have less willpower? The operational variable, the dependent variable is level of cigarette smoking, but cigarette smoking, yes, no, is binary variable as compared to the independent variable amount of willpower. So along these lines, you need to think when it comes to the operationalization. It's just important that you recognize and know that. Also, it's important that you know how to distinguish between comparative studies and correlational studies. Correlation is basically where you quantify associations. That is correlations and regression mainly. Comparative studies are these hypothesis tests that we do. The t-distribution, set distribution, analysis of variance. These are comparative studies. Then also make yourself acquainted with research designs that you have basically when you have an experimental study as opposed to an observational study. You basically have a study with an experimental component. So you have an intervention and you do random assignment to reduce the amount of confounding. And confounding is, it's nicely illustrated with this example, which we discussed in a bit more detail, where we have self-selection into a wellness program. So where basically you give an employee the possibility to enroll him or herself in the wellness program. And then as the outcome, as the dependent variable, you study health behavior. So if you have these two, these are your independent variable at two different levels. That's your dependent variable. If individuals can self-select them into your level of the independent variable, you will have a lot of confounding because those that end up in the wellness program are more likely to be the healthier and people that are just in a better, healthier shape. And those that are not in the wellness program will have self-selected, in the no health wellness program will be the less healthy individuals. So thereby your analysis of the outcome will be confounded or biased. So just know the reasons for that. Also, we made the comparison in terms of age. So you remember on the homework you had problem 3 with the different age groups. So you saw that there were differences in the age, and then you mapped it out. And like this is the kind of analysis you need to think of. You want to tease these differences out, and you do that with graphing, or you do that by randomization and various other means. So these are confounding influences. And then in the same context, we also have between groups design and within groups design. Between groups design is where you compare, so that's the comparative study. Within groups design is where you do correlational analysis over time, or you have a within groups design like a paired sample t-test where the independent variable is actual time, or you have within groups analysis of variance where you basically follow several groups over several observations. Just make yourself comfortable with these terms, please, before the midterms. Data ethics and open science, talked about all of this. All right, just meant to explicitly discuss those briefly. That's pretty much all I had for today. Any questions? If not, have another evening. See you on Wednesday.